So, I, you know, so we're saying population here, right? So can you read this? So P is population, yes? So what's it saying? The population is doing what on the left side? In that equation, what's the left-hand side saying? What's happening with the population? What the hell is a derivative? Sure, or decay. So how it's changing, right? So my population on the left-hand side is changing, but it's equal to some constant times the population. So meaning the population could be doubling, right? Uh, Half-life, radioactive decay, half the population, right? So we're just thinking about what does this particular answer look like, okay? So the way it's changing, I can see a whole family of functions here, right? If k is 1, I get one curve. If k is 2, I get a second curve. If k is 3, I get a third curve. And that's one of the first things we're going to do is once we get our differential equation, take a look at it. It's kind of hinting at to me what the solution is, right? Like just look at that orange line or that purple line, right? It looks like an exponential. Oh, but think about an exponential. When I take the derivative of an exponential, I get an exponential again, but times whatever coefficient I had in my exponent, right? The chain rule. So you can really see, oh, if I get my same function back, well, how many times do I get my same function back when I take a derivative? Not many, right? There's a couple of really cool ones, but of course the exponential is the simplest one we see. So what we're trying to do is actually find the solution of it, right? And of course, it'll be obvious what we do. We're going to integrate. We're going to integrate to find the solution, right? So, but if I just take a look at even if I just draw the original function, and that's how we're going to start, right? So for example, let me go this way. Let me go Desmos. Oops. And let me say y equals e raised to the minus kt, or kx, and I'm going to add a slider k. So what I'm asking you to do is kind of burn this line into your memory, right? You're kind of trying to burn that line into your memory, and then we're looking at all of those other possible functions. Here's the one that they had, right? So we're kind of burning all of those things into our mind of what's happening. And what I'm actually doing is right here is I'm drawing tangent lines along the curve. So I'm drawing tangent lines along the curve. So I'm drawing tangent lines along the curve. And what I end up seeing is something called a slope field. I'm giving an overview here, okay? So slope fields, I'm pretty sure I know which one I like on this one. So in GeoGebra, please feel free to join me here. And I'm searching for slope fields. I think he's from Argentina, the one I like. I don't know. Yeah, Marcos? Yeah, I like that one. Even though it's one of the ones before, but it's fine. He copied it. It's okay. I definitely want one where I can see several things. I have to be able to put in my diffeq, okay? I have to be able to put in the differential equation. I don't care too much about the vector length or the spacing. It does make it sometimes easier to see. But what's really important is that I can see this initial value and I could change the initial value. So meaning I know the point 0, 1 is on my curve. I can see the original function. Now, this is my original, this is my answer. This is not the diffie-q. This is the equation, original equation. So meaning I've integrated already, okay? But if I draw slopes along that, tangent lines along that, can you see that I'm in the groove of a bunch of arrows? So that my red line is in between a bunch of the arrow. I like to think of it as like water flow, right? So I can see where the water would flow. There's rocks or whatever diverting it in a particular way. And so the green arrows are me drawing tangent lines on the original family of functions. So I can find the original function. I don't know which one is the one I want, but I can draw the slope field on there and I know it's got to fit in one of those grooves, right? So you'll be using this slope field a couple of times. This is a good one. If you find another one, if you like it, that's fine as well. But you need to be able to put in the function. You need to be able to, it's nice, you want to be able to find the original solution, right? And I'll talk about that a little bit later. So anyway, we had an answer of e to the minus kt, right? Oh no, my diffie-q was, forget it, I didn't even have one. I can't put in kp, it's not going to understand it. I need x's, or kx still doesn't make a lot of sense for me to do that. Anyway, so the first thing we talk about in our textbook is that we should be able to find a solution, right? It won't always happen in real life, in our applications in real life. When I'm doing chemistry, I might notice a pattern of how something's changing, but not be able to come up with the equation. But I still can predict it for the future. So that's a big part of what we're going to be doing. So there's another diffie-q, right? A second derivative. Here's a nice one to do. So let's start here. So I've got y prime is x times y. I'm going to go right to my slope field and put in x times y. So there is one possible solution. As I move this point around, you can see my other possible solutions in that slope field, right? Kind of looks like what shape do you? Yeah, it kind of looks like a parabola. Let's see what happens when we actually solve it. So again, we're just talking in general, what's the diffie-q here, right? So I had y prime equals x times y. And I can see the slope field for that right away. Not without GeoGebra, right? I'm going to go to GeoGebra. I want to be able to visualize the slope field and visualize maybe one particular answer. Of course, this is dy dx equals xy. And when I have a product or quotient of a function and a variable, this is called a separable equation. I can turn this into dy over y equals x dx. Sorry, separable. They tell us that later in the book, but I don't like keeping secrets. I like to read the last page of the book first anyway. So I know it's coming. I can get there pretty quickly. Look at what happens on the left side, right? And the right side. So now each side is its own little world to us, right? The left side, I'm following my same old rules all the time, but with a variable y. Same thing on the right-hand side. Usually it's going to be x on one side, and we're always so comfortable with that. And clearly, this guy on the right is simple, right? It's x squared over 2 plus c. So you can see my quadratic. You see the quadratic, right? Or you said quadratic, right? You said parabola? Yep. And but what happens on the left? I get the ln of the absolute value of y. All right, that's a little bit weird. And so it's gonna change my idea of the parabola a little bit, because how can I get rid of the ln piece? Raise both sides to base e. Right? So e to the ln of the absolute value of y is e to the x squared over 2 plus c. So I just get absolute value of y equals e to the c times e to the x squared over 2. What I'd really like to do is try and figure out what piece is not changing at all, right? So, and then maybe even rename it. So I get y equals, if I get rid of absolute value, what do I need to include? Plus and minus, yeah. So I get something like this. It's pretty typical for me to change something that's a constant into one single character, one single variable. Exactly. It's some other constant, exactly. And you'll see the book use certain things at times. They'll use a K for a constant with a K, right? Or C for a constant with a C, or etc. A sometimes. So, but this, so now what I want to do with this is I want to actually graph this with different values of K and see on Desmos to see if I get a same kind of mirroring of the slope field, right? So to Desmos, I don't think I need the plus minus because of K is any variable. So if I slide it to a negative, it will give me the negative, right? So K e raised to the x squared divided by 2. And a slider K. And you can already see it does have a kind of a parabolic shape to it, but there's a little squareness to it. And you'll see what I mean by the squareness when if I change, right? If I get really close to 0, it kind of squares out a little bit, right? But you definitely can see the same. In fact, the bigger K is, the more it looks parabolic to me, right? But there's my negative piece as well. And so what's kind of nice is if I know at one point on the curve, I'll be able to figure out K and then graph that actual one. And that's where this GeoGebra piece comes into play. If I know my function hits the point 0, 2, right? If I know my function hits the point 0, 2, then I know that 2 equals plus or minus K e to the 0 squared over 2. Oh, okay. So K is plus or minus 2, right? But it has to be positive, obviously, right? So this is giving me K is 2. So I know the actual answer is 2 e to the x squared over 2. This guy is called the initial value problem. So meaning if I know some point on my original curve, right? If I'm solving a differential equation and I know the location on the moon when I want to land, I can then figure out where that path leads me, right? Yeah, that's the idea. If I know where I want the solution to end up, and it's feasible, right? It's in the domain, that type of thing, then I can figure out the exact equation that I want. Or, you'll see later, get a really damn good estimate for it. We just did the whole chapter, so I gave you the overview of everything. What's a differential equation? How to solve it. So we saw me separate x's and y's and integrate. How to think about, right, a slope field as the family of functions, right? And then maybe find the initial value. And the only thing that I haven't talked about here is something called Euler's method, where he shows how to get a good estimate of a diffie-q that you can't actually solve, right? So, but we will go there. All right, let's take a look at a couple of the problems of interest in this section. And so I'm going right to 7.1. So sometimes we're going to be verifying solutions. Right now, remember how we first learned parabolas or quadratic formula, and we would say, well, the answers you should be able to plug back in. We're doing the same thing here. We're going to take an answer to a diffie-q and see if it works, right? And then see if we could generate more solutions from a given solution. So let's just look at number 2 here. So it says verify that I have a solution for the initial value problem given to me. I just want to take a picture so I don't have to keep. So number 2. Well, here's the thing, is that most of this stuff that we're doing is for modeling, and so that T is standing for time. What's the bacteria population with respect to time? Yeah, I agree with you, though. It's annoying. Yeah. Exactly. Let's just make it a Z, because I feel like it, yes. So T times dy dt equals y plus t squared sine t. And so, and we're saying that we got an initial value, sorry, we got a solution of minus t cos t all minus t, right? So I want to verify that that works. Well, so meaning I've got the answer. I want to see if it fits in my diffie-q. Well, it's pretty clear that I can put the y value in here, right? And I could put the y value in here as long as I integrate. Sorry, differentiate, sorry, right? So I'm going to take the derivative of that to see if it works and plug it in. So I already know I'm going to have t times the derivative equals negative t cos of t minus t plus t squared sine t. Right, you with me? And if it feels easy, it is easy. All I'm asking you to do is plug in a solution, right? So I plugged y in where I could. I got to plug in the derivative of y as well. So I want to be thinking of the derivative of this. Remember your product rule? Derivative of cosine is negative sine, right? Yeah. Anybody else get the same derivative? Do you want to see me do a product rule? Yes? Yeah, so I'll just show you how I teach my Calc 1 students product rule. So if y equals f times g, or y equals f divided by g, so product rule, quotient rule, right? I do f prime, g prime, and I get a p with a positive sign in between. So you see I get f g prime plus g f prime. Of course, you could just memorize that, but I like the loop, makes it kind of nice. Because when I do quotient rule, I do the same thing, but I'm getting the letter q, and then I've got to get a g squared as well. So y prime in this case is g f prime minus f g prime all over g squared. So that loop just gives me a nice little shortcut. So what did we had? We had t cos of t? No, negative t cos of t, right? So negative t and negative 1, cos of t, negative sine of t, right? There's my product rule. Yeah. Right, so if you see this first diagonal, I get a t sine t, and then I get a minus cos t, right? Yeah? Of course, if you can do it without my method, do it without my method. So anyway, this is going in here, right? T sine t minus cos t minus 1. And then when I distribute, it's obvious. What's today, Tuesday? I'm planning 7-1 today, 7-2 on Wednesday, 7-3 on Thursday. No quiz Thursday, right? And then we come back. We don't, remember, we're off on Monday. I'll start chapter 8, which won't hurt at all because 8-1 and 8-2 are just review of sequences and series. And then we'll review on the Wednesday and test on Thursday, right? All right, so first thing in the book is, can you verify that you have the solution to the Diffie-Q? The next thing that we'll do is something like 4A and B here. So, I mean, I can already kind of tell you, you know, you should try odd problems in 7-1.
In 2, it also gave us that y of pi equals 0.
So the initial value, sorry, yeah. Let me go back to that. So I do have an initial value here. So if I put in 0 for this particular piece, right? I should get. Should I get pi out of it? I'm sorry. Let me think. Yeah. So this y of pi equals 0 is telling me, and if you look at my initial solution, you see there's no kind of constant in there that would change the family. You know what I mean? T is the variable t. I would need like an A or a C value to say that I hadn't yet solved for that value. And so it's kind of irrelevant that they give me the initial value there.
Okay. Just making sure.
Yeah, it's not a bad idea though to put that one into, for number two, put the diffie-q in to GeoGebra, and then put in this the initial point 0 pi, right? 0 comma 3, about 3.14, and then I should see that exact function that they gave me the y equal. So that's not a bad thing for you to do. But anyway, let's look at number 4. It says, for what values of k does this function satisfy the differential equation, right? Yada, yada, yada. So, so here I'm going to have to solve for k, and then I'm going to do something with the value of k. So I have for k equals question mark, y equals cos of kt satisfies 4 y double prime equal 25y. Let me just double check that I have that right. Negative 25y. 4 y double prime equal negative 25y. So again, it's an initial value problem, but it's not an initial value problem. It's a differential solution to a differential equation, but it's the general solution. It's got a k in it. I want to figure out what are my restrictions on that particular value. So anyway, it's pretty clear that I have to plug in the cos of kt. I also have to plug in y double prime, right? So let's find y prime. What is that? Negative k sine of kt. Is that agreed upon? Right? Derivative of cosine is negative sine, and then the derivative of kt is k. And then y double prime is what? Negative k squared. Derivative of sine is cosine, right? Cos of kt. Yeah, exactly. So now I'm plugging all of that into my original diffie-q because it's saying it should satisfy it, but then I want to figure out something about k. So what do I get? I get a negative 4 k squared cos of kt should equal negative 25 cos of kt. So it looks like obviously I have something that's factorable, so it looks like I'm probably going to do that. But we're trying to figure out what we get for k, right? So anyway, let me move everything to one side. 25 cos of kt minus 4 k squared cos of kt equals 0. Say again? I lose a variable if I do that, right? But I can definitely factor out my cos of kt, and I get 25 minus 4k squared. And so this is just back in 8th grade again, right? Or whatever grade it was for us. For me, it was 9th, 10th, and 11th grade. I took algebra. But I know cos of kt equals 0, and I know 25 minus 4k squared equals 0. So I'm setting each of those up. The second part, of course, is easier. What is it? 25 fourths. So k is plus or minus 5 halves. The other one takes a little bit more thought. I need k to get me a guaranteed 0, right? But I know cos equals 0 whenever I'm what? Yeah, odd pi over 2's, right? So 1 pi over 2, 3 pi over 2, etc. So k is going to be equal to
They don't really use K.
yeah, 2n minus 1 times pi over 2, odd pi over 2. So 2n minus 1 or 2n plus 1 will give you an odd number.
Yeah.
2n minus 1 is a generator. So if I did this guy, first thing, second thing, third thing, fourth thing, and then put in my odds, I would generate a y equals mx plus b. That would be a 2n minus 1, yeah. So this is a 2n minus 1 if I do my y equals mx plus b on it. Right, just so obviously there's the minus, right? So there's that b value, and then the slope, of course, to pick any 2 points and you get a slope of 2.
You do 2n to make sure it's even, and then subtract 1 to make sure it's
Exactly.
Okay, yeah.
Yeah. The next thing in the problem is what's interesting. It says now that I know the restriction on k, right? And so I can use k as 5 over 2, negative 5 over 2, or any odd pi over 2, 7 pi over 2, etc. I don't know if I like this answer. I'm thinking. Give me a second though. But certainly the 5 over 2 minus 5 over 2. It says verify that if I plug into this solution, I also get a solution, right? Now, how we're finding those other solutions is coming later, okay? In the Diffie-Hughes course, not this one, okay? So, but it's interesting just to put the 5 halves in there, right? And then verify again. So meaning do what? All right, plug in the original solution with the k values filled in, find the second derivative with the k values filled in, and then plug in again, and it should work, right?
Right.
So there's a bunch of things like that. I probably will ask you from 1 to 7 odds. So when I assign homework for Tuesday, I will assign chapter 7 homework. It's not going to be difficult, and you'll see it's just taking more antiderivatives. Yeah, I definitely like 1. I like 3. I like 5. I like 7. So you can do a rough sketch, and then if I assign one of them, you can rewrite it, right? Nice. Let's take a break. Let's come back at 10. Okay.